Hey guys, welcome back. Week two here. We're going to start talking about something called a confidence interval for a proportion. All right, so confidence intervals are the next big topic here. Hopefully, last week with the sampling distributions, hopefully those went well for you. Again, remember if you have any questions or anything, make sure you're emailing me, messaging me. I'm more than happy to help you out with more personalized questions if you have them. All right. So let's start talking about this confidence interval thing. You probably heard in the news about this deadly virus, COVID-19. So I kind of made a set of notes that are kind of about that, right? To kind of talk about definitely a topic that's on all of our minds right now, and how statistics kind of plays into that. Okay. Um, I've had a lot of arguments with friends and family centering around what the actual percentage of people who have had or currently have a COVID-19, right? So, like, is it 10%? Is it 20%? Is it 5%? A lot of people believe that the percentage of people that have COVID-19 is much higher than what the news is reporting or that we actually know. And it's difficult to accurately determine what the actual percentage or what the actual proportion of people with this disease is. All right, and not being able to get an accurate picture of what this virus is doing or how many people actually have it really does impact our ability to fight it. All right, so some of the reasons that we are not able to get this accurate number is one, not everyone is tested, right? So a lot of people don't exhibit symptoms, so they would not bother to get tested. They don't get the sore throat or the difficulty breathing or anything like that, so they just kind of continue on with their daily life, thinking they're fine. So they would never actually ask to be tested, or nor would they go to a hospital for testing. All right. The bad part is they're still contagious. So they walk around with COVID-19 not even knowing it, and they spread it, which is why they're telling us all to stay home because we don't know who has it and who doesn't. All right. Second thing is there's just not enough tests to test everyone. All right. There probably never will be. There's like 7 billion people. It's never going to be feasible to get a COVID-19 test to all 7 billion people. All right. And then there's just a lot of skepticism about whether or not certain officials or certain news reporting agencies are being honest with the numbers that they have. Okay, so some people might do a bunch of testing. They're like, oh my gosh, this is going to cause panic, or this is going to scare a lot of people. So they might report kinder numbers. But there's no evidence that anyone's actually doing that. But it's certainly a possibility that people could be dishonest with the data that they have. Okay. So the question is, can we use what we know about the normal distribution to calculate how accurate an estimate might be? And as it turns out, we can. We're going to be looking at something called a confidence interval, which attempts to capture the actual proportion of people who have had COVID-19. Okay. So for instance, the question we're trying to answer is, what is the actual proportion of people that have this disease? We might answer it with an interval. Like we might say, well, I don't know the exact number, but it might be somewhere in between 8 to 12% or 40 to 50%. Right? We're not going to be able to answer it with an exact number. Instead, we'll give an interval that attempts to capture the actual number. Like we're going to be somewhat confident that the actual number is in between 40 and 50%, or that the actual number is in between 8 and 12%. I don't know what that actually is yet. Okay. So that's what a confidence interval is. It's an attempt to capture the actual number inside of an interval of two other numbers. Okay. So how do we start? Well, as with any statistical experiment, we've got to start with data. All right. So we're going to gather data, and we would use one of the random sampling techniques that we talked about at the beginning of the year. All right. So maybe a cluster sample or a systematic sample, or maybe a combination of several different sampling techniques. But we would go out and we would essentially determine a random sample, and then we would test people for COVID-19. All right. So we're going to pretend that we did that because I don't actually want you going out there trying to test people or anything. So just pretend that you did it. And let's say that we sampled 1,000 people, and 483 of them, of the 1,000 that we sampled, had COVID-19. All right. So 483 out of 1,000, which gives us a sample proportion of 0.483. Remember, we don't actually know the true proportion of people with COVID-19 by only looking at the sample. This is not the population proportion. This only pertains to our sample. And if I were to go out and sample a different 1,000 people, I would come up with a different proportion. All right. And if I went out and sampled a third set of 1,000 people, I would get yet another different proportion. And this should feel familiar to what we were doing last week, and where we take samples of 1,000 over and over and over again. And every sample of 1,000 that I take gives me a different proportion. Right. But if I were to take those proportions that I got every time I took a sample, and I were to create a distribution with them, it would create a normal distribution. Right? That's what we talked about last week. Right? So when we talk about this down here, when we talk about this shape, okay, we would get a shape for our sampling distribution. Here's our shape, and it would be normal because the size of my sample was sufficiently large. We took 1,000 people, and if you recall from the central limit theorem, sufficiently large was 30. Okay, so this is what our shape would look like. And forgive my pen here, I'm still getting used to this tablet. All right. So this number, this 0.483 that we came up with from our sample, this is what we would use as a point estimate. We would go ahead and assume that this is the center of our distribution. So when I draw the shape of my distribution, I'm going to draw something that's normal because we had 1,000 people in our sample. And I'm going to go ahead and mark the center of this thing to be 0.483. Okay. I'm going to scoot down here. And we can say, all right, our sample proportion is 0.483. And notice that I put that little hat, we call that a hat, on top of the P here. That's to indicate that this came from a sample, not the population. All right, so this is what we call our point estimate. All right, important vocabulary word, that's why it's bolded and underlined. All right, the next thing we're going to calculate is our spread. Right, what is our standard error? And you might recall from last week, the way that we did that for a sampling distribution was we took whatever the proportion was from the population. In this case, this is our best guess, is 0.483. So we're going to take that 0.483 and we're going to multiply it by its complement. Right, so 1 minus 0.483. And then we're going to divide by the sample size, which is 1,000. And then we have to square root this thing. Okay, this gives us our standard error, which is kind of important. So I'm going to pull up my calculator here, and I'm going to, there we go. I'm going to go ahead and calculate this. So I got 0.483, and then in parentheses, we have 1 minus 0.483, and I'll hit enter, and then we'll divide by 1,000. Okay, and then we'll square root that. There we go. So we got 0.0158. Yep. So now we have the shape of our sampling distribution. We know it's normal. We know an estimated center, and we have an estimated standard error here that we're going to use to help us carry on with this confidence interval. Okay, so let's go ahead and go to the next page here, and we're going to start talking about actually creating this interval. All right. So before we do that, we got to kind of think about normal distributions and how they work. So we're going to kind of draw on a couple of things here from earlier on in the semester, and think about what does it mean to create, like, let's say, a 90% confidence interval. And what that means for us is that inside of our normal distribution, we're going to try and capture 90% of our data. All right, so think about any normal distribution, not just our sampling distribution from the front page, but any normal distribution. Let's say, hypothetically, we have a normal distribution here, and its center is 0. All right, so we know the mean here is 0, and we're going to say a standard deviation equals 1, right? So this is a standard normal distribution. What we're trying to find is the boundaries, or are the boundaries, let's say here and here, that would contain 90% of our data, right? We're trying to capture 90% of the histogram. So if I were shading this area underneath the curve here, okay, we would want this area to be 0.9, all right? And we got to figure out what boundary values would do that for us. All right, so if we have 90% of our data contained here in the middle, that means each of these tails would contain 5% of our data, right? So we'd have 5% in each tail. And this is like a custom made problem for inverse norm, right? So if I did an inverse norm, I can figure out what those values are. Right? So I'm going to do an inverse norm, and I'm going to do a 0.05 and a mean of 0, standard deviation of 1. Okay? And you can do that on the calculator yourself. But what you're going to get is a negative 1.645 if you round to the third decimal place there. So this value over here on the left would be a negative 1.645. Then using a little bit of symmetry, I can come over here and say this is going to be a positive 1.645. All right. So really what this is telling me is that to get 90% of my data captured in the middle here, I would have to go 1.645 standard deviations to the right, and I would have to go 1.645 standard deviations to the left. And that's where I would set those boundaries. All right. These numbers, this 1.645 and negative 1.645, they call this a critical value, right? So this is another vocab term that we need to pay attention to, these critical values, all right? That's why it's bolded and underlined. And they have a notation for critical values. It's a z with a little alpha over 2, okay? And we're going to say that z alpha over 2, or our critical value, is plus or minus 1.645, okay, indicating that we have to go that many standard deviations to the right and to the left to get 90% of our data inside of those boundaries, right? And these boundaries represent our interval that we're trying to create, okay? So just might want to mark this in your note. These are the critical values. Okay, so why do we care about the critical values? Again, well, again, they tell us how many standard deviations away we have to go, but we can use them to calculate how far we have to go in our distribution, right? So remember, our distribution on the front page looks like this. It's normal, but its center is not 0, right? Our center was 0.483. But we still want to contain 90% of our data. We want to get 90% of those proportions within these two barriers here, right? So if I were capturing this, we would have 0.90 of our data in between those two values. We would still have 0.05 or 5% in each of our tails, and we're trying to find these two values, okay? So to figure that out, we have to figure out how far to the right of 0.483 do we need to go. Well, we know that we have to go 1.645 standard deviations to the right. So I can take that 1.645 and I can multiply it by whatever my standard deviation is from the front page, which was 0.0158, right? And if I multiply those, I'm going to get 0.025911. So this is the distance that I need to go to the right over here, right? So if I were going from 0.483 to where this x is, this distance is 0.025911. And to go over here, let me scroll down a little bit. And to go from here over to this x value, darn it, stupid pen. So if I were to go from here back to my center, this distance would be negative 0.25911. All right, so that's how far we have to travel to get to those boundaries there. All right, and this number that we just calculated, this thing is called a margin of error. Okay. And we did that by taking the standard, or the critical value, z alpha over 2, and multiplying it by our standard deviation from our sampling distribution. Okay, we call that the standard error. All right, so we now know how far to go. We know where the boundaries of our interval are going to be. Let's just take a minute here and kind of summarize some of the things that we have found. All right, so one of the first things we found was the point estimate, right? Notation, p hat. Okay, so p hat we found by taking that 483 and dividing it by 1,000. Okay, and we got 0.483. Then we started analyzing the shape and the center and the spread, and we found the standard error. So remember, we found that by taking p hat times 1 minus p hat and dividing it by n, and then square rooting that whole thing. And what we got when we did that calculation was 0.0158. This tells us about the spread of our sampling distribution. Okay. The next thing we figured out was our critical value, right? Notation was z alpha over 2, and we did this using an inverse norm. Okay, we did the inverse norm, and we found ours to be plus or minus 1.645. Right, then we used the critical value to calculate a margin of error, and we did that by taking our standard error and multiplying it by our critical value. Right, so this is the general thing that we did, and what we actually found was 0.025911, and we established that our level of confidence for this was going to be 90%. Right, you'll usually get that in the problem, and we can turn that into a decimal at 0.9. All right, so we actually have like all of the important information that we need to construct our interval. We have it right now, and that's what we're going to do next, is actually express our interval. There's 3 accepted ways to do this, right? And the first one I'm going to show you is this plus or minus notation. This is the one that the news companies use all the time, and the most common one that's disseminated to the public. Okay, so when we do a plus or minus notation, we start with the point estimate. So we say 0.483, and we're going to do plus or minus. So 0.483 plus or minus the margin of error. So I'm going to say 0.025911. All right, so we would say we are 90% confident that the actual proportion of people with COVID-19 is 0.483 plus or minus 0.025911. Okay, now the way the news is going to say this, they're going to do some rounding, and they're going to kind of express this in a way that's more common for people. So they're not going to say 0.483. They're going to say 48% plus or minus, and let's say 2.5%. Okay, so they're going to round a little bit. They might say 2.6, whatever. But essentially what they would say is we're 90% confident that 48%, or I'm sorry, we're 90% confident that the actual proportion of people with COVID-19 is 48% plus or minus 2.5%. All right. So this next way that we're going to express it is with an interval. All right, and the way that you get your interval is you actually go ahead and do the plus or minus part, right? So we're going to take this 0.483, and we're going to express this like an ordered pair. And to get the lower bound, let's say the lower number here, we're going to take 0.483 and subtract the 0.025911, and we'll get an answer there. So we'll get 0.457 for that one. And then I would do the same thing, but this time I would add, so 0.483 plus 0.025911. I would add those two, and we would end up getting 0.509. So we could say we're 90% confident that the actual proportion of people who have COVID-19 is in between 0.457 and 0.509. All right, the last way we're going to express this is with an inequality, and you're going to notice when I set this up, we're going to say P, but with no hat, because we're estimating what this is. Okay, this is an estimate of the actual population proportion. So we're saying the actual population proportion is somewhere in between 0.457, and 0.509. Okay? So numerically and symbolically, these are the three accepted ways to express that confidence interval. And then the last step here would be to interpret it. All right, so when we interpret that 90% confidence interval, we always start with this. We say, I am 90% confident that. And you would say something, I'm 90% confident that the actual population proportion is between 0.457 and 0.509. All right, so you actually do have to talk about this in words when you get to the quiz or the test. I'm going to ask you to interpret a confidence interval, and you're going to have to write a statement like this. All right, and the most common mistake that students will make is they will say there's a 90% chance or there's a 90% probability the actual proportion is in between 0.457 0.509, and that would be wrong. All right, that do not mention probability, do not mention chance, do not mention anything like that in this statement. A confidence statement is different than a probability statement. Okay, so do not say probability or chance in here. Also, make sure that you're indicating what it is you're estimating. All right, we're estimating the actual population proportion, so you want to include the word all or population somewhere that indicates that you know what it is you are estimating in that statement, and then tell me what the interval is in English. Okay, so real quick, just a quick discussion here about what does this confidence level actually mean. Okay, and this is some abstract stuff here. So we're going to kind of switch away from the problem that we were talking about on the front two pages and just talk about a 75% confidence level in general. And for this talk, we're gonna assume that we actually know what the population proportion is. Okay, so for this example, we know that the population proportion is 0.80. Okay, so let's say I go through that process that I showed you on the first two pages. I go and I collect a sample and I construct a confidence level or a confidence interval, and this blue gap right here represents that interval that I found. Okay, so from here to here, that is my confidence interval that I constructed, and the actual population proportion is this green dotted line. All right, so this confidence interval that I constructed, the green dotted line runs through it. So my interval would have captured the actual population proportion. But let's say I did the experiment again. Let's say I went out, I collected data, and I construct a new confidence interval based on my new data. I would not get the same interval that I got the first time. But instead, let's say I got this interval, the second bar that we see here, and notice that this time I did not get the population proportion. Okay, and then let's say I do it a third time, and this time I did, and the fourth time I captured it, and again and I captured it, but then I get down to this one and I didn't capture it. All right, so what's going on here is every time I create this confidence interval using the process that I just showed you, I either get the proportion or I don't. Right, so it's like when we're looking at these first two, I got it here, I didn't here. So the probability that I actually have the population proportion within the interval that I created is either 0% or 100%. All right, and that's why that confidence level that we're talking about is not a probability. All right, it doesn't tell you the probability that your interval contains it or it doesn't. That can only be one of two numbers, 0 or 100. All right, what this is telling me when they say 75%, you saw how that related to the critical values that we calculated. And in simpler terms, what it says is if I were to perform this experiment 100 times, I would capture the actual interval 75% of the time. Right. So in other words, if I ran it 100 times, 75 out of the 100 times that I create a confidence interval, those 75 confidence intervals will contain the population, the actual population proportion. Okay, and I know that's really abstract and difficult to understand sometimes, Uh, but just remember, it's not a probability, and all it's telling us is how often the experiment will capture the population proportion, which is a little bit different than a probability that the interval you have has the proportion. Okay. All right. I'm going to end the video there. Let that sink in a little bit. You might want to go and try some of the problems using that process that I just showed you. And probably take a day before you watch interval or the second video for this thing. Okay. All right. Have a good day, guys.